Here's a function, it's a parabola. What does the inverse of this function look like? That's the question for today. So first of all, before we talk about the inverse, let's just plot some points from this function in this little table of values here. So just from the graph, there's basically 3 points we can draw, that point, and that point. So let's just write down the coordinates of those points. The first one's going to be -3 and 1. So just going over here a little bit, we have -3 and 1. That's the first coordinate. The next coordinate, we have -2 and -1. And the third coordinate is -1 and 1. Cool. So what does it mean to take the inverse of f of x? What that means essentially is we're inverting the x and the y values, or we're just swapping the x and the y values, or the f of x and the x values. So in our function, we have our first point as -3, 1. In the inverse function, these are going to be switched. So it's going to be f of x is going to be 1, and then the inverse of f of x is going to be -3, right? So this is sort of like just saying what was that x value of the original function, right? Our second one's just going to be switching those around, so -1 and -2, and our third point is going to be 1 and -1. There we go. So now let's plot that inverse function just based on those 3 points. So our first one is 1 and -3, so it's going to be down there. Our second point is going to be -1 and -2, which is going to be right there. And our third point is going to be 1 and -1, so it's right there. And if we just do a quick sketch of this, or connect the points of the curve, we're going to get something that looks something like that, right? If we can imagine those 3 points making sort of a parabola on its side. So how are these two graphs related to each other? We know the coordinates are related to each other because the x and the y's are switched, but how does the graph relate to each other? And the idea is that all the x coordinates are mapped onto all the y coordinates, right? We switch the x and the y. So it's like we've taken all the x and we've made them equal to y. So all the x equal to the y values. So essentially what we're doing is, what this looks like graphically, is that we're reflecting it in this line x equals y. X equals y is just an equation of a line, right? With slope 1 and a y-intercept of 0. So essentially we're just reflecting that. So imagine that line being a mirror, and we've just sort of flipped it over to the other side. If you turn your page sideways or like on a 45-degree angle, you can see very clearly that it's just reflected in that line. So this equation, the equation of the graph we have graphed here, the red equation, is listed up here. It's 2x plus 2 squared minus 1. So we know that's a quadratic in vertex form, right? So the question is, how can we determine the equation of its inverse? And there's a few ways to do that. We're going to start off with this way, the inverse order of operations. I actually really like this method. So to do this, let's just copy down this equation like that. So there's our equation, 2x plus 2 squared minus 1. That's our f of x. So let's think about what's happening to the x in this equation in the correct order. So say we plugged in a number for x, what would we do to that number? First of all, we would add 2 to that number, right? Because it's x plus 2, so we would add 2. And then what we do is we'd square that whole number. So we'd do x to the power of 2. We'd square it. Then what we do is we'd multiply it by 2. So we're going to multiply by 2. And then the last thing we would do to that number is subtract 1. What the inverse does is the inverse essentially undoes all those things, or it reads them in the opposite order. So if that's our function f of x, the inverse of f of x is going to start from the bottom, and it's going to read those and do the opposite operations. So the first thing, if we would, the last thing we did to that f of x is we subtracted 1. So the first thing we're going to do to the inverse is we're going to do the opposite. We're going to add 1. And then the next thing we're going to do is instead of multiplying by 2, we're going to do the opposite of that, which is dividing by 2. The next step that we're going to do is, instead of squaring it, what's the opposite of a square? And the answer is square root. And then the last thing we're going to do, if we look, is we plus 2 in our, we added 2 in our original, so now we're going to subtract 2. So the way we can use this to come up with the equation of our inverse is we just follow these steps. So for example, the first thing we did to our x value is we added 1, so x plus 1, and then we divided that whole thing by 2, and then we took the square root of the whole thing, and then we subtracted 2. Do you see that? So just running through that one more time, we added 1 to x, and then we divided what we get by 2, then we square rooted the whole thing, and then we subtracted 2. So see, you just do the opposite operations in the opposite order. So this, and we call this f negative 1 of x, right? The negative 1 is our symbol for inverse. It's not actually an exponent there. It's just little notation that tells us inverse of f of x. So that's the way to do it with opposite operations. Unfortunately, this method doesn't work when we have more than one x in the equation, like it was like a quadratic x squared plus 2x plus 3. We couldn't use this method because there's multiple x's in there, and it's really hard to write out what the order of operations would be when there's multiple x's. So that's when we have to turn to this other method, which you will see here. And this is just how we algebraically do it. So here's our f of x again, and essentially what we're going to do is exactly what we did when we graphed it, and all we did when we graphed it is we switched the x and the y values. So if we, instead of f of x, if we call this y, right, so I'm actually going to just replace this with a y, we're going to switch the x and the y values, and it's going to look something like this. X equals 2y plus 2 squared minus 1. So that's our inverse, right there. Now notice, we could be done here, right? Because that's our inverse. The problem is that we have a y squared. And usually when we're doing, when we're thinking about whether something's a function or not, a y squared tells us it's not actually a function, which is true in this case. So what we like to do it is we try to turn it into a function by isolating y, right? Because it's much easier to graph something if we have it y equals. So let's isolate y. So first thing we're going to do is we're going to get that 1 to the other side, x plus 1 equals 2y plus 2 squared. Then we can divide by 2 to cancel out this 2 here, right? Then we can square root, right? To get rid of that square here, we can square root the whole thing. So what we're left with is this root x plus 1 over 2. And then, by the way, we're going to move this 2 to the other side, right? And it's going to be subtracting 2 like that equals y, right? So if we isolate for y, that's what it's going to look like. So we might think we're done there. If we zoom out a little bit and look what our previous answer is, these actually are exactly the same, right? This one and this one are exactly the same. So we might think we're done. But a way we can check is if you throw that into Desmos. And if we throw this equation or this equation into Desmos, we are not actually going to get this blue graph here, this inverse. Instead, what we're going to get is just part of it. We're going to get the top part like this. And that's a problem because that actually doesn't represent the whole inverse, right? That only represents sort of half the inverse. So what's the problem here with our algebra? So going back down here, the problem with our algebra is taking the square root. Whenever we take the square root, we have to be, of both sides of an equation, we have to be very, very careful. Because thinking about it very simply, say we had the equation x equals, x squared equals 4, something like that, right? In order to solve that equation, we would have to take the square root of both sides, essentially, right? Square root and square root. And if we do that, we're going to get x equals 2, obviously, right? But is that the only thing that could give us 4 as an answer? And the answer is no. There's actually another solution to this problem. X could have been negative 2 as well, right? Because negative 2 squared also gives us 4. So that tells us that the answer to this equation actually should be plus or minus 2, right? One way to actually see this as well is think of it like this. X squared equals 4 is an equation. We can solve that equation by setting it to 0 and factoring, right? So 0 equals x squared minus 4. That's a difference of squares. So we would factor it like x minus 2, fix that, hold on, x minus 2, x plus 2. So there's our two solutions to this, right? X equals 2 and -2. Okay, so this simple looking equation here actually has two solutions of +2 and -2. And it's the same thing when we go back to our equation here. When we take the square root of both sides, there's actually going to be two answers for each value of x, or sorry, for each value of y. So what we have to do is in front of that square root, we have to put a plus minus sign. So the actual full inverse of the function has two parts. So we would write it like this: f(-1) of x equals the positive root, which would be like this, root x plus 1 over 2. That whole thing should be under the square root like that, minus 2. And another root, which looks like this, negative root x plus 1 over 2, minus 2, right? So essentially we have, and we usually use curly brackets to indicate there, we essentially have two answers or two parts to this function. Now, is it actually a function? The answer is no, it's not a function, right? It doesn't pass our vertical line test because it has two parts. But if we looked at each part individually, each of those parts individually is a function. And that's what generally we're going to be focusing on when we do some math with these things. We'll be looking at one part at a time. So taking a step back to our previous answer over here, we have to consider the same thing. We can't just call this the final answer. Whenever we take a square root using this process, we should always be doing the plus and minus answer to that to get our full complete answer. So the important properties of an inverse are listed here on your page. As we saw in the last one, the inverse of a function might not be a function. A function is a mapping of x to y. We know that. You're just switching x and y. Graphically, the line is reflected in y equals x. The notation looks like that with a little -1, which again is not an exponent. It's just notation that tells us it's the inverse. And this is important actually. The domain of the function is the range of the inverse. And the range of the function is the domain of the inverse. This makes sense because you're essentially just switching the x and the y values. So the domain and the range also just switch. So let's do the first example here, finding the inverse of each of these functions. We're just going to do this by very quickly making a table of values and plotting the points. And then we'll also algebraically determine the inverse if we can. So let's just make a table of values from -2 to +2. I think that'll be enough to give us a sense of this function. So complete the table of values, and I will do that here as well. So here's just that table of values for our f of x. So let's just quickly sketch that as well based on those points. So that's roughly what our f of x looks like, right? It's just essentially the base cubic function shifted down by 1. So that makes sense. Let's now create a table of values for our inverse. And you can probably predict what the inverse is going to look like. If you remember, it's just going to be reflected in y equals x. But let's make that table of values just so we can plot those points easily. So there we go. There's our inverse, our table of values for our inverse. Notice I just switched the x and the y coordinates. Now, graph the inverse. So there we go. That's what it looks like. You see I labeled it f(-1) of x as the inverse in red and f of x as our function in blue. If we just very quickly draw in that line, y equals x, we can see that it looks like it's reflected in that line. So we probably didn't make any mistakes when we did this. So that's okay. One other thing I want to do that the question doesn't ask us to do, but I want to talk about the domain and range of each of these functions. So very simply, if we look at f of x, we say the domain is x is an element of real numbers. Are there any restrictions? No, it's just the entire set of real numbers. The range is y is an element of real numbers. Any restrictions? No, it goes from -infinity to +infinity. Is it going to be any different for the inverse? And we know no, because essentially what's going to happen is the domain and the range are going to switch, right? So the domain of the inverse is going to be the same thing as the range. X is an element of real numbers. We have to keep the x and the y. The x is always for the domain, and The y is always for the range, but the values are going to swap. In this case, it doesn't really matter. It's pretty boring because both of them are just an element of real numbers. Okay, and that is for f negative 1 of x, the inverse. Okay, the last thing we should do here is determine algebraically or otherwise the equation of the inverse. So to do that, we're just going to do it algebraically. So we know f of x equals x cubed minus 1. And the inverse, we're just going to swap the x and the y, right? So again, this f of x, we're going to call that y here. And swap them. So x equals y cubed minus 1. And then we just have to isolate for y to find it explicitly in terms of y. So we can just do that y cubed, I'm just going to switch it around, equals x minus, oh no, x is going to be x plus 1, right? If we just rearrange that a little bit. Now we have to isolate the y by getting rid of that cubed, and the inverse of a cube is a cube root, right? And that gets rid of that cube there. Now the question I have for you is, do we need to put that plus minus in front of that, right? Or is the answer just y equals the cube root of x plus 1? Should I put the plus minus? Well, again, let's take another little example on the side, right? So I'm going to say, what if our equation was x cubed equals 8, right? How would we solve that equation? And we would solve that equation essentially by taking the cube root, right? Just as we just did, the cube root of 8. So x equals, the cube root of 8, if you do that on your calculator, is going to give you 2, or you know that 2 times 2 times 2 is 8. Is it possible there's another solution to this? Like, could you use negative 2? What's negative 2 cubed? Negative 2 cubed actually ends up being negative 8. So the idea is here, the sign can only possibly be positive here for this 2. There's no negative root there. So when we're doing a cube root or any odd numbered root, we actually don't have to do the plus minus. It's only when it's an even number of root. So this is our final answer there. And is it a function? In this case, it is. And we can see that from the graph, right? Definitely looks like a function. And the reason is because it doesn't have that positive and that negative side to it. So here we have the last question, and I want you to try this one yourself. What I want to remember is I want an equation, right? An equation for of f negative 1 of x. I want a graph for f of x and f negative 1, negative 1 of x. And I also want you to give me the domain and range for f of x and f negative 1 of x. So do those in any way you see fit, and then unpause the video. So pause the video and then unpause it to see the final answers. So here is our final answer. I've graphed f of x in blue, f negative 1 of x in red. So there's the functions. Makes sense. One is a parabola on its side, or basically 2 square root functions. And then we have our equation of our inverse down here. Notice it's not actually a function because it's got those 2 separate roots, the top root and the bottom root. It's just a relation. Lastly, our domain and range. So for our regular function, our domain is going to be x is an element of real numbers, such that, oh, again, do we have any restrictions on x? No, we don't, actually. So I can just, let me erase that. So that is our domain. And our range on our function is going to be y is an element of real numbers, such that y, well, we know y has to be less than this maximum value up here of 2, right? So y has to be less than or equal to 2. There is our range. So if we look at our inverse now, I'm going to do that in red, what is going to be our domain and range? And if you think about it, let's actually just look at the graph for a second. Our x values are all going to have to be to the left of 2, right? So it's going to be like that. And our y values can be any value, right? Because this graph can keep on going forever and ever. So the only restriction essentially is on our x value. And notice how that's just essentially flipping these two domain and range of our regular function, right? Because the domain is now going to be x is an element of real numbers such that x has to be less than or equal to 2, and our range is just going to be y is an element of real numbers. So you see, the domain and the range just end up switching places for the inverse, which makes sense because we're essentially switching all the x and all the y values. There we go.